And welcome back to 13.4 podcasts. We are looking at phase diagrams now, where we're going to try to predict the physical state of a particular substance at various temperatures and pressure. And right now we're looking at a phase diagram of water. This is further on in your chapter 13, your 13.4 notes. And what we want to do is we want to show you how you can actually predict the changes that are going to take place with a particular substance as you change pressures and temperatures. So we are currently, let's pick a point. We're going to pick this particular point right here on the diagram. 101.3 kilopascals is 1 atmosphere of pressure, and that's a normal pressure to have under normal conditions. All right, and if you notice this particular line right here, this is denoting 0 degrees Celsius. So if you're at normal pressures below 0 degrees Celsius, you're going to be, water anyway, will be a solid. Now, if you increase the temperatures, eventually you're going to hit this slanted line on the phase diagram, and you're going to be going between a solid and a liquid, and eventually you'll be melting the ice into water. And you already know that that's going to happen. So you have the melting that takes place right there. Once you get done with the melting process, you're going to be heating up your water, and it's going to get warmer and warmer and warmer until it hits 100 degrees Celsius, right? Once you hit 100 degrees Celsius, then it's going to start to boil, and it's going to stay there until all the water has boiled, and then you're going to move into the gaseous phase, or vapor. So at this point in the diagram, you're at a solid. Anywhere in the green area, you're going to be liquid, and then once you cross that barrier, you're going to be a vapor. Now, the other thing that you can do as, say, a liquid is you can lower the pressure. Let's label these, by the way. Let's say that this is A, point B, and point C. And we are back at point B. We're at, with liquid water at somewhere between 0 and 100 degrees Celsius. This looks like it'd be at about 50 degrees Celsius because it's right in between there. What you can also do is you can change the pressure. What if we start to lower the pressure? You're still at 50 degrees Celsius, but you're lowering the pressure. Eventually you're going to cross that phase boundary again, and the water is going to start to boil. Believe it or not, water can boil at temperatures that are less than 100 degrees Celsius. And in fact, you can get water to boil at 50 degrees Celsius if the pressure is low enough. Notice you're getting to pretty low pressures, but the water will in fact boil. Now, why is the water boiling at this point? Remember, in order for something to boil, the vapor pressure has to match the atmospheric pressure. Well, if you're lowering the atmospheric pressure, it takes less heat or less temperature to achieve that vapor pressure. And so as you lower this atmospheric pressure, eventually you're going to match the vapor pressure and the water is going to boil. We'll call that point D. All right? Now you can continue to lower the pressure. And let's just say we're right here at point E. It is still a gas. You can lower the temperature. If you lower the temperature, cold, get it colder, get it colder, get it colder, you're still a cold gas, but notice it does not even turn into a liquid. Eventually you run into this phase diagram, or this phase boundary here between the solid and the gas, and the water's going to actually deposit from a vapor directly into ice. It will not be liquid water. We'll call that point F. You can increase the pressure. Once it's a solid, you can increase the pressure higher and higher and higher. You're at 0 degrees Celsius. Eventually, you're going to be back to your melting. You can actually compress the ice into liquid water. Now, that's actually unusual. Most of the time, you're going to compress a liquid into a solid, but ice is unusual for reasons we'll get into in just a second. In fact, why don't we explain this right now? As you increase the pressure, this is a real weird thing with ice. Eventually, you're going to get back to your melting of the solid into a liquid. The reason why is pretty simple. Most of the time, liquids, I'm off to the side here, most of the time the liquids are fairly far, not far apart, they're fairly close, but they have a little bit of distance in between them. But as you squeeze them, apply a pressure, you're going to get them so close together that they start sticking together and lining up in a very orderly fashion, and you have your solid. That's the norm. Okay, that's not actually what happens with water. The reason why is simple. Ice, or liquid water, forms ring structures. Here's your H2O. It's not exactly like this, but I think you'll get the point. Actually, that should be a dotted line. We'll go dot, dot, dot. Dot, dot, dot. And we'll continue on until we can finish this off. And that's close enough. It's not exactly what the structure looks like, but it gives you the idea. When you have ice, H2O forms these ring structures. Okay, it's actually more of, I think it's a hexagon. I have to look at the diagram, but it is a ring structure with a big empty space in here. Okay, when you start to squeeze the solid from all sides, what you do is you actually break these interactions among the water molecules, and therefore, if I scroll down just a little bit here, I don't want to get off the page, but what happens is the water gets, or the ice gets squeezed so that all the molecules are kind of fitting closer together, which in the case of H2O, that's water, the liquid phase. So it's very rare that this occurs, but water is one of the substances that actually does this. So this is a liquid, while this was the solid. So you're squeezing the solid into a liquid, which is unusual. Normally, if I scroll back up here, normally this is what happens, where the liquid gets squeezed into the solid. Alright? In just a second, we'll be taking a look at the phase diagram of carbon dioxide.